As I said in the last video, we're going to look at the remainder theorem, which will lead us to the factor theorem here. Let's go ahead and move through that. The remainder theorem says the remainder of f of x divided by x minus c is equal to f of c. Let's take a look how we use this. Use the remainder theorem to determine f of 1 given f of x equals 3x to the fourth minus 2x cubed plus x plus 4. Well, what the remainder theorem says is if we divide that function, 3x to the fourth minus 2x cubed plus x plus 6, and we divide that by x minus 1, then whatever we get, the remainder on that is going to be equal to f of 1, because we are dividing by x minus 1. So these c's match. Is that what we did up here? It is x to the fourth minus 2x plus x plus 4. Notice we got, in our answer here, we got 3x to the third plus x squared plus x plus 2 plus x minus 6 over x minus 1. The remainder was 6. That tells us f of 1 is equal to 6. Now, there is absolutely no reason why a person would ever evaluate this function at x equals 1 using this technique where you do the long division and then, even with synthetic division where it's much faster, and then find the remainder and recognize that. You're just going to plug 1 into this function and get 6 from it. But it's going to lead us to something else. So let's do this one more time just to see exactly what we get here. This says evaluate f of 3, where f of x equals x to the fourth minus 3x squared plus 9x minus 81. That means I want to divide that polynomial f of x by x minus 3. It says do it using synthetic division. I don't want to do long division on this if I don't have to, so let's do the synthetic division. 1, I need a 0 for that missing cubic term. -3, 9, -81. We put the 3 over here, and I put a little box around it to distinguish it from these other values. Draw a horizontal line, leave some space. The 1 comes straight down. Then I multiply the 3 by the 1 and put it here. And I add, and I get 3. Multiply the 3 by the 3 to give me 9. I add and I get 6. Multiply the 3 by the 6 to give me 18. I add, I get 27. Multiply the 3 by the 27, I get 81. I add and I get 0. This last number is the remainder. These other numbers are my coefficients on that division. I divided an x to the fourth by an x, so I'm going to have x cubed plus 3x squared plus 6x plus 27. That's what this is equal to. Okay, with a remainder of 0, that tells us that f of 3 is equal to 0. The second part of this is to check that using the actual function. So let's plug 3 in. We have 3 to the fourth minus 3 times 3 squared plus 9 times 3 minus 81. 3 to the fourth is 81. That's minus 27 plus 27 minus 81. We get 0 because we got 81 minus 81 and 27 minus 27, right? So we get 0 when we check it by evaluating a function. If I gave you this function and asked you to find f of 3 This that we just did right here probably makes the most sense as the best way to do this. It's intuitive to us. It makes sense because that's what we do with functions. We're looking to evaluate a function at a particular number. We plug it in. So, but we do get the same result whichever way. So I suppose you could evaluate functions using synthetic division if you chose. The value in this is that when we get a remainder of 0, we know, based on what we talked about before, that we could do something like multiply both sides of this top equation up here by x minus 3 and now we get that this f of x is equal to the product of these two polynomials. And we also get that x minus 3 is a factor. If x minus 3 is a factor of this, then x equals 3 is a 0. So what we get here is f of c equals 0, meaning c, by definition, x equals c is a 0 of f of x, if and only if x minus c is a factor of that. So kind of working through the idea that if f of c equals 0, then we get that remainder equal to 0. If the remainder is equal to 0, then it becomes a factor. And so the value here is that once we know something is a factor, x minus c is a factor, we know c is a 0, and vice versa. So we can work the other way. Hopefully this isn't really a surprise to you. When you factor something like this, these are the zeros because x minus 1 will give us x equals 1 is a 0. X plus 1 will give us x equals negative 1 is a 0, and so on. One way this is helpful is if you know the zeros, we can write some function f of x. If x equals 3 is a 0, x minus 3 has to be a factor. If x equals negative 2 is a 0, x minus negative 2 has to be a factor, or we would probably just commonly write that as x plus 2. This function that I have written here is a function with zeros, x equals 3 and x equals negative 2. It's not unique, it's not the only function with those zeros, but it is a function that meets those conditions. The reason it's not the only function is because, say for example, this could be squared and this to the 7th power, and it still satisfies those conditions. You could have an 8 in front here, and it doesn't, I guess, explicitly say that those are the only zeros, so I guess you could have other factors here. On a quiz or test, it would be more, or on a test, it would be more explicit. But, so that's kind of using the factor theorem kind of the other way, is once you know something's a 0, then you can write the factors too. Let's use this as an example, or look at this example. This function is not something that we know how to factor using traditional factoring techniques. Normally when I see 4 terms, I think of factoring by grouping, but factoring by grouping will not work here, because if you group those, you get x squared times x minus 2. If you pull out the negative, that's really the only thing that you can pull out. Factoring by grouping only works if these match, and they don't here. So factoring by grouping does not work. We have to try something else. Well, let's kind of guess here and see if we can find something that will help us factor this. Remember, factors are also going to be zeros, which are going to give us a remainder of 0 using the combination of that remainder theorem and the factor theorem. So we want to divide by something. Let's just pick something. Let's try 1. Let me write my coefficients. 1, -2, -5, and 6. Bring the 1 down. We multiply 1 times 1 to give me 1. -2 plus 1 is -1. Multiply, we get -1. -6, multiply, you get -6, you add, you get 0. Well, I got lucky, right? I picked x equals 1 as a potential 0. Really, what I picked was what I found was that x cubed minus 2x squared minus 5x plus 6 divided by x minus 1 is equal to x squared minus x minus 6 using these coefficients right here, or these numbers as the coefficients over here. What that tells me is that this f of x function, x cubed minus 2x squared minus 5x plus 6, is equal to x minus 1 times x squared minus x minus 6 if I multiply both sides of that equation by x minus 1. So I've gotten one step towards factoring this, and hopefully, now that I have a quadratic here, can I just factor that? Sure, x minus 3 and x plus 2. This question asked for that function in factored form. Finding that one factor really helped us here because it got us down to a quadratic that we could then further factor. The question also asks us to solve that polynomial equal to 0. So set this equal to 0. Each of those factors gets set equal to 0. You get x equals 1, x equals 3, and x equals -2. Are the solutions to that equation? They would also be x-intercepts of the graph of f of x. I think that answered that question. So I hope you're starting to see the relationship between either long or synthetic division. I just find synthetic division easier. You can use that. If you get a remainder of 0 there, that means it works as a factor. X minus 1 would be a factor of this polynomial if we get since we got remainder 0. It also tells us, so because it divides evenly, it's going to be a factor. We know it's a 0 of the polynomial. We know x minus 1 is a factor. So you get a lot of information when your remainder is 0. If your remainder is not 0, you got to try something different. We got lucky here. The first thing that we checked did work. So there's that. There's a little note down here at the bottom that says kind of what I summarized at the end of the last video was everything in the previous videos factored for us or was given to us in factored form. This one, I got lucky, right? Sometimes that's okay. Guess and check is an okay thing and you get lucky and that's okay. But that could be very frustrating because there could be a million different things that we try and none of them work. So we'd like to have some more sophisticated methods for what we should guess. And we do have theorems that help us with that. So that's where we're going to be going from here, is to that idea that I don't want to just guess random things because I could guess a ton of them. So hopefully we'll get some good logical guesses. So stay tuned for that.